Hello everyone. In this second module of current electricity, we are going to discuss about some basic definition, mobility, current density, conductance and conductivity. Second, microscopic form of Ohm's law, or we can say vector form of Ohm's law. Third, limitations of Ohm's law. Fourth, resistance and factor affecting resistance. And mainly temperature dependence of a carbon resistor. And finally, color code for carbon resistor. So let's start. So first of all, basic terminologies. First, mobility. Mobility, which is noted by mu. The mobility of a charge carrier is the magnitude of drift velocity acquired per unit electric field. The magnitude of drift velocity per unit electric field. And Vd, we already know Vd is equals to tau small e capital E upon m. This relation between electric field and drift velocity. So we are replacing Vd with tau E capital E upon me. Mu is equals to tau E upon m. If the moving charge particle is electron, so we can replace E with electron, charge of electron, or if a moving particle is a hole or any other particle, we can replace this E with that particle. So this is our relation between drift velocity, mobility and relaxation time. So SI unit of mobility is meter square per volt per second. Next, current density. Current density. So always remember, current is a scalar quantity, but current density is a vector. Current density is a vector quantity. Current density is the amount of charge flowing per second per unit area normal to the flow of charge. So current density is equals to current per unit area, which is equals to current is equals to charge per unit time upon area. So in general form, J is equals to I is equals to J dot A or J A cos theta. SI unit of current density is important, ampere meter per meter square. So again, what is current density? Current density is the amount of charge flow per second per unit area normal to the flow of charge. And finally, conductance and conductivity. Conductance, third number, conductance. Conductance is reverse of resistance. Which is denoted by G, which is equal to 1 upon R. Conductance of a conductor is the ease with which a electric charge flow through it, or it is equal, numerically equal to resistance. कितनी आसानी से कोई चार्ज फ्लो कर पा रहा है, ये हमें कंडक्टेंस बताएगा. Similarly, conductivity is reverse of resistivity. The reciprocal of resistivity of a material is called conductivity. It is denoted by sigma. This is our fourth basic definition. Our next topic, vector form of Ohm's law. Vector form of Ohm's law. So if E is the magnitude of electric field in a conductor in which is battery is placed across it. Let A is a cross section of this conductor, L is length, and E electric field flowing through it. So if E is the magnitude of electric field in a conductor of length L, then the potential across this conductor is equals to V equal to EL. This is a simple relation between potential and electric field. And we also know V is also equals to I into R according to Ohm's law. Ohm's law के according V equal to IR होता है. And R can be replaced by rho L upon A. Rho L upon A. So compare in first and second. EL is equals to I rho L upon A. L to L cross. E is equals to I A rho, where IA is known as current density. So E is equals rho J. E equals rho J. Okay. So E equals rho J, and rho is equals to 1 upon conductivity. J equals to E. So J is equals to sigma E. This is microscopic form of Ohm's law. J equals to sigma E. So the next topic, we already know general form of Ohm's law, which is equals to V is directly proportional to I. It is stated that current potential across the conductor is directly proportional to the current at a constant temperature, where this proportional is replaced by R. This R is known as resistance of the conductor. So actually resistance is the property by virtue of which a conductor opposes the flow of charge through it. रेजिस्टेंस एक वो प्रॉपर्टी है किसी कंडक्टर की जो करंट के फ्लो को रोकती है, मतलब वो इलेक्ट्रॉन को फ्लो होने से रोकता है, अपोज करता है। अगर इलेक्ट्रॉन फ्लो नहीं होगा तो आपका इलेक्ट्रिसिटी कंडक्ट नहीं होगी उस कंडक्टर में से। ऐसा यूनिट ऑफ रेजिस्टेंस इज ओम, symbol omega. The factors affecting the resistance are following. First, length. Second, area of cross section. Third, nature of material. R equals to rho L upon A. Sigma denote resistivity denote resistivity depend upon nature of material. Nature of material. Resistivity also known as specific resistance. Specific resistance. The resistivity or specific resistance of a material may be defined as the resistance of a conductor. So rho is equals to R A L upon L. So the resistivity or specific resistance of a material body may be defined as the resistance of a conductor of that material having unit length, unit cross section area, and its unit R is noted by omega, meter square upon meter. So ohm meter is a SI unit of resistivity. Effect of temperature first for the different we are discussing temperature dependence for the following materials. First, metal. Second, semiconductor. Third, insulator. First of all, you already know that resistance of a conductor is a property by which it opposes the flow of current through it, and the basic cause of the resistance is collision. When potential is applied across the conductor, its free electron get accelerated. On their way, they frequently collide with the positive metal ions or different free electrons. That is, their motion is opposed and its opposition to flow of electron is called resistance. The main cause of resistance is collision. Larger the number of collision per second, smaller is the relaxation time. and larger is the and larger will be the resistivity, because rho is equals to m tau e tau. So larger is the number of collision per second, smaller is the relaxation time, and larger will be the resistivity. So if we increase the temperature of that conductor, suppose this is our conductor, this is our conductor. If we increase the temperature with the help of a burner, in the case of metal, the number of free electron is fixed, but as the temperature increase, the amplitude of the vibration, यहाँ बेटा वाइब्रेशन आपके और बढ़ जाएंगे इस एक्सटर्नल एनर्जी की वजह से. सो द एम्पलीट्यूड ऑफ द वाइब्रेशन एटम इंक्रीजेस, बिटवीन द एटम्स इंक्रीजेस. जितने ज़्यादा वाइब्रेशन बढ़ेंगे वो आपस में और कोलाइड होंगे. द कोलिजन ऑफ इलेक्ट्रॉन विल विथ दीज एटम बिकम मोर फ्रीक्वेंट. जैसे जैसे टेम्परेचर बढ़ाता जाऊंगा ये और बढ़ता जाएगा और बढ़ता जाएगा. तो आपका एक फ्री इलेक्ट्रॉन को यहां से यहां मूवमेंट करने में जो पहले टाइम लगता था टाउ, अब वो बढ़ जाएगा. सॉरी, एक्सटर्नल एनर्जी मिलने की वजह से इसका जो रिलेक्शन टाइम था यहां से यहां मूवमेंट का टोटल टाइम, एवरेज टाइम, वो कम हो जाएगा. अगर आपका एवरेज टाइम कम हो गया तो आपका टाउ बढ़ जाएगा. अगर टाउ इंक्रीज हुआ तो आपका रेजिस्टेंस इंक्रीज हो जाएगा. तो सिंपल सा है, इलेक्ट्रिकल रेजिस्टिविटी ऑफ अ कंडक्टर increase with increase the temperature and consequently resistance of that conductor. Second, for semiconductor, in the case of semiconductor, the relaxation time tau does not depend with the temperature, but the number density of the free electron is increased exponentially with the increase in temperature. The case of semiconductor, tau doesn't depend upon the temperature, but n depend exponentially. For example, the case semiconductor, let's take example of silicon. So silicon में एक्सटर्नल सिलिकॉन कोवेलेंट बॉन्ड बनाता है. जब एक्सेस एनर्जी इनको मिलती है तो इसके बॉन्ड ब्रेक होते हैं. तो आपका नंबर डेंसिटी ऑफ द इलेक्ट्रॉन इंक्रीज एक्सपोनेंशियली. ब्रेक होने से नंबर ऑफ इलेक्ट्रॉन इंक्रीज हो जाता है. सो फाइनली उनका रो डिक्रीज हो जाएगा. सो ऑन इंक्रीजिंग टेम्परेचर number density of free electron increases, hence resistivity of semiconductor decrease with the increase in the temperature. Third, For semiconductor like carbon, germanium, silicon, with the increase in temperature, the number density increases but the relaxation time decreases. Number density increases but relaxation time decreases, but the increase in n compensate more than decrease in tau. आपका n ज्यादा पड़ता है टाउ से, तो फाइनली n compensate more than decrease in tau. So finally, insulator, the electrical resistivity increase exponentially with the decrease in temperature. In case of semiconductor, this is our graph. On increasing temperature, the electrical resistivity decreases exponentially. There's a relation between previous resistance and the final resistance after increasing temperature. Suppose RT is the temperature, RT is the resistance after increase of temperature, and R naught is the initial resistance of that conductor. 1 plus alpha T. Here alpha is known as temperature constant, temperature coefficient. So RT is the resistance at T degree Celsius, and R naught is the resistance at 0 degree Celsius, and T is the rise in temperature. For metal, alpha is positive, and for metal alpha is positive. For semiconductor, alpha is negative, and for alloys like constantan and manganese, the temperature coefficient of the resistance alpha is very small. These are temperature independent resistors. चलो इनको सबको ग्राफ से एक को एक्सप्लेन करते हैं. तो आप इस रिलेशन से आर टी इज इक्वल्स टू आर नॉट 1 प्लस अल्फा टी से, सपोज आपका पास एक रेजिस्टर है जिसका रेजिस्टेंस प्रीवियस रेजिस्टेंस ये था, ये आपको वैल्यू गिवन होगी. इट इज कांस्टेंट क्वांटिटी विच डिपेंड अपॉन द नेचर ऑफ मटेरियल. सपोज आपने उसको कुछ टेम्परेचर इंक्रीज कर दिया, तो फाइनली उसका जो रेजिस्टेंस होगा वो इस रिलेशन से हम फाइंड कर सकते हैं. Let's sketch graph showing the variation of resistivity and with the following material with temperature like copper, second nichrome, third semiconductors, any semiconductor. For copper, the graph is like this: resistivity with respect to temperature. For nichrome, the graph is like this. For semiconductors or insulator, the graph is like this: rho T, rho T. Finally, limitation of Ohm's law. There are two types of conductor called ohmic and non-ohmic conductor or resistor. Ohmic conductor which obeys Ohm's law V directly proportional to I. The conductor which follows Ohm's law is known as ohmic conductor, and non-ohmic conductor which do not obey Ohm's law are called non-ohmic conductor. In this situation, the graph is like sometime like this, sometime like this. At higher temperature, these metallic conductor doesn't follow Ohm's law. So at higher voltage or higher temperature, for the sum of the materials, Ohm's law is not followed. At higher voltage, sometimes some metal do not follow Ohm's law. Finally, carbon, color code of carbon resistor. This is of a carbon resistor. इसमें जो स्ट्रिप्स हैं ये डिफरेंट कलर्स की होती हैं, 4 स्ट्रिप्स होती हैं और हर एक स्ट्रिप का अपना अपना एक कोड है. इस कोड की हेल्प से यू कैन इजीली आइडेंटिफाई द मैग्नीट्यूड ऑफ द रेजिस्टेंस ऑफ दिस कार्बन रजिस्टर. So, color code of resistor. Color code of carbon resistor. This is carbon resistor. So, for black, brown, red, orange, yellow, green, blue, violet, gray, white. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. एक सिंपल सा ट्रिक है. बीबी रॉय of Great Britain have very good wife. B.B. Roy of Great Britain have very good wife. Suppose आपके पास एक कार्बन रजिस्टर है जिसमें 4 कलर कोडिंग है. जो फोर्थ होता है ये सिल्वर हो सकता है, गोल्ड, सिल्वर. फोर्थ स्टेप गोल्ड, कैन बी गोल्ड, सिल्वर और नो कलर. दिस स्ट्रिप इंडिकेट टॉलरेंस पावर, कितना ये इसमें करंट टॉलरेट जा सकता है, कितना टॉलरेट कर सकता है विदाउट बर्निंग इट. नो कलर, तो इसके लिए हम यूज करेंगे 5%, 7%, 10% एंड 20%. ये है भैया हमारा कलर कोड ऑफ रजिस्टर. याद करने का सिंपल ट्रिक, बीबी रॉय ऑफ ग्रेट ब्रिटेन हैव वेरी गुड वाइफ. ब्लैक, ब्राउन, रेड, ऑरेंज, येलो, ग्रीन, ब्लू, वॉयलेट, ग्रे, व्हाइट. सपोज आपके पास कोई 51 रजिस्टर है जिसका फर्स्ट बैंड है येलो, सेकंड बैंड है वॉयलेट, थर्ड है ब्राउन और लास्ट फोर्थ स्ट्रिप है उसका लेट गोल्ड। तो फॉर येलो इसको जो रिप्रेजेंट करने का सिंपल सा मेथड है, डैश डैश मल्टीप्लाई 10⁻⁻⁻ डैश प्लस माइनस डैश। यहां हर एक डैश एक कलर है। स्टार्ट करेंगे हम लेफ्ट हैंड साइड से, येलो 4, वॉयलेट 7, ब्राउन 1 प्लस माइनस गोल्ड 5%। तो 47 into 10 raised to power 1 ओम प्लस माइनस 5% इसका रेजिस्टेंस वैल्यू।